So every conference has three most difficult talks for the speakers. The first talk, the last talk, and the first after the conference dinner. So that's my role today. Now, I want to start with the following elementary question. So suppose we have a graph, gamma. Graph. And the question is, what elements of the first homology group, let's say H, are realized by embedded circles. So you have a graph, you have an element of a homology group, you ask yourself whether it is represented by a circle embedded in the graph. Now, first of all, the question has nothing to do with orientation of the circle. So if a class is represented, that minus this class also is represented. So as a result, it's enough to consider homology with coefficients in Z2. Now let's consider a few examples. Let's start with this graph. So that's the graph with one vertex and two edges. Now the homology group, of course, is Z2 squared. Z2 plus Z2. It has two natural generators, one the loop on the left and the loop on the right. So let these generators be A and B. So A and B obviously are represented by embedded circles. So A and B, yes. But their sum, no. So you can see that their sum, of course, they're represented by a circle, but the circle is not embedded. And the zero class is never represented by embedded circles, so we may forget about zero. Okay, let's consider this example. That's another graph. Now we have two edges, two vertices and three edges. Now homology group is still the same, Z2 plus Z2. Again, there are two natural generators, A, B, and their sum. And all these three homology classes, all these three non-zero homology classes are represented by embedded circles. So one circle is this one, same on the right, and this external circle. So the answer is yes for all non-zero homology classes. Okay. Now these two examples already teach us something. If you look at these two graphs, you see that they are homotopy equivalent. Right? If you collapse this edge, the middle edge, the point, you get the graph on the left. So the question and the answer to this question are not invariant of homotopy type. So homotopy type of a graph is insufficient, and you need something more delicate. Okay?
But in that example, like initially said that we don't care about orientations, I can go from Z to Z from two coefficients. That's a bit cheating, isn't it? Because like here, in that example, if you sort of take
no, I mean, this homology class, for example, is
but you're saying, oh, we don't care about orientations, I can just go from Z to Z more two coefficients.
Yes.
But that was cheating, wasn't it?
No.
No, but here, like if you take like the graph on the right, like if you take the class which shows wing like that.
No, for example.
A little one twice,
The answer to the question depends only on the homology class modulo 2.
No, because A plus B.
Yes. A plus B is this. This class in whatever direction.
But you take say A is almost like on the left.
Okay, that's too complicated, right? You want something with the...
You see, because if you do that for two coefficients A plus B equals A minus B, but this A plus B might be representative, but A minus B might not be representative. Fine,
Yeah, I understand. But what I wanted to say is only that if homology class is represented, yeah, you are right. Maybe I was too quick. But anyway, I will consider only homology classes modulo 2. No? It was not a mathematical statement. Okay. Now I'm going to switch from topology to algebra and discuss algebraic structures that arise when you think about this question. So the homology is algebraic structures involve the notion of a partial order. Partial order. So I just recall that the partial order is a bilinear inner set. Let's say inner set X. So that's binary relations such that, first of all, any element is smaller than or equal to itself. If A is smaller than or equal to B, and B is smaller than or equal to A, then they are equal. And if A is smaller than or equal to B, smaller than or equal to C, then A is smaller than or equal to C. And this, of course, is called reflexivity. This is what? Symmetry, and this is transitivity. So that was the notion of partial order. A set having a partial order is called a partially ordered set, which is for brevity called poset. So a poset is a partially ordered set. And partial ordered set is a set with a fixed partial order. All right. Now I'm coming to something new. So motivated by this question, I want to consider so-called additive posets. So what is an additive poset? An additive poset. So additive poset is an abelian group. Abelian group, let's say A, with partial order. And this partial order should satisfy two requirements, such that. Now, if you have three elements, so for any elements A, B, C of the group, if B, so there are two conditions. If B is smaller than or equal to A, and C is smaller than or equal to A, then B plus C is smaller than or equal to A. And the second condition, if A is smaller than or equal to B, and A is smaller than or equal to C, then you can guess A is smaller than or equal to, I think it's better. Плохо видно. Okay. So if A is smaller than or equal to B and A is smaller than or equal to C, then A is smaller than or equal to what? B minus? Stavros would make you vote, and then would take this, you know. Okay, so A is smaller than or equal to A plus B plus C. A plus B plus C. So that's the definition of an additive poset. Now, I don't know whether it is new. I tried to find this definition in the literature, and I failed. So I consider it's a new notion. If not, let me know. All right. So this is a notion I need to answer this question about graphs, and which arises from this question. So what I'm going to do now, I'm going to give examples of additive posets, and I will talk about elementary theory of additive posets, some related notions, and then I will come back to graphs and also to CW complexes. So additive posets arise quite naturally from algebraic considerations or from topological considerations, and we'll see both. Now, before going further, I just want to state a couple of properties of additive posets. So one property, which is, let's say, a lemma, which says that if A is an additive poset, so for any additive poset A, additive poset A, and any element of it, A plus A is equal to 0. So it follows from these axioms that all elements of an additive poset have order 2. So in fact, it's a vector space over Z2, necessarily, just corollary of these axioms. And also what we have is that the zero of the abelian group is the least element. So 0 smaller than or equal to A. And 0 is smaller than or equal to A. So in fact, it's about vector spaces over Z2. So no point in trying to consider something more complicated so far. All right, now examples. Let's just take Z2. A is equal to Z2. There are two elements, 0 and 1. And we just say that 0 is smaller than or equal to 0, smaller than or equal to 1, and of course, smaller than or equal to 1. So this is a partial order which satisfies these conditions. And I call it trivial partial order. So that's a trivial partial order. Trivial. Of course, this can be directly generalized. Instead of Z2, you take any vector space over Z2, any vector space over Z2. And then you say that 0 is smaller than any element for all. For all elements of A. And of course, A is smaller than or equal to A. So this defines a partial order which satisfies all the conditions. So that's again trivial, but A may be any. All right, a more interesting example. A more interesting example is you start from an arbitrary set. Let's see. You start from an arbitrary set, I, and you consider its power set, 2 to the power I. So it's a set of all subsets. Of I. Now what is the partial order? That's just inclusion. So if you have two subsets, X and Y, subsets of I, then X is smaller than or equal to Y if X is contained in Y. Now what is the addition operation? It's just symmetric difference. So X plus Y is X minus Y union Y minus X. The symmetric difference, and all axioms are satisfied. Now, this might look a little strange, but if you think about this set of all subsets, let's just for simplicity of exposition, suppose that I is finite. What I said doesn't use finiteness, but just for this discussion, 2 to the power I is nothing else than the direct sum of Z2s numerated by elements of I. What is a subset of I? It's a function which assigns 1 to elements of the subset and 0 to all other elements. So it gives you an element of a vector space with basis I and with coefficient ring or field Z2. Okay? Such an element is a linear combination of elements of I. You have coefficients, you have only ones and zeros. So those coefficients that are equal to 1 determine a subset of I. So this power set is nothing else. And this addition, the obvious addition, term-wise, is the same as symmetric difference. So the fact that this is an abelian group actually is obvious. And the fact that there is such a partial order is also obvious. But in fact, the two axioms that are stated also are satisfied. So this is an example of an additive poset. Now, this is a key example. So if there are questions on this? Okay. Now, how can you get further examples? One thing is that if you have an additive poset, then you can provide many more examples by taking sub-posets. Now, let me explain this. So if you have an additive poset A, additive poset, well, let's say, in fact, I need to write the symbol for the partial order, though usually I don't do it. So if you have an additive poset and you have a subgroup, let's say B, a subgroup of A, then I can restrict my partial order to B, B with a restriction. It's also an additive poset. also an additive poset. And that's obvious, right? Because if the axioms hold in A, they hold in B also, for elements of B. So every subgroup of an additive poset also is an additive poset. Now, starting from here, you can consider additive posets by taking just subgroups or subvector spaces of this vector space. Now, how many are they? That's another question. I'm going to give some kind of construction which shows that there are many. But this kind of posets that are subgroups of the power sets are the most important for topology. All right. Now I want to give another construction of additive posets. Which is supposed to persuade you that there are many of them. So the construction goes as follows. Let's start from any vector space H. So H, vector space over Z2. And let's take any subset S of the dual vector space. S is just a subset of the dual vector space, which consists of all homomorphisms from H to Z. Now I'm going to define a partial order in H. So for any AB in H, we define by definition A is smaller than or equal to B if S of A is smaller than or equal to S of B for all S, for all elements S of this set S. For S in capital S. Now, what does it mean? So an element S is a homomorphism from H to Z2. So this guy is an element of Z2. This is an element of Z2. And in Z2, remember, we have this trivial partial order, which I mentioned at the beginning. So we can write this. So if this condition holds for all S in my set S, then I write that A is smaller than or equal to B. So that's my definition. And the claim is that if S, the big set S, generates H star, then what we get here is, I switch to another chalk, then what we get here is an additive poset. So then H with this partial order, actually it is a partial order, is an additive poset.
Is it possible to consider homomorphisms not to Z2 but to another A?
Yes, it is possible. Yes. So this is an additive poset. So each time when you have a a subset of the dual vector space which generates this vector space, for example, which means it includes a basis, then you get an additive poset. So this construction shows that in some sense there are many of them. There are many of them. And of course, different sets S may give different additive. This is a trivial partial order in Z2, the one I defined at the beginning. T stands for trivial. Okay. Now, there is a question. Okay, before giving a question, let me give a definition. So I define the class of additive posets. So I call an additive poset is plane, so definition. Definition. An additive poset is plane. Is plane if it can be obtained by this construction. If it can be obtained by that construction. Зеленым. Ну, попробуй зеленым. So if it can, yes, зеленый бета, can be obtained by that construction, or in other words, one can say if it is a additive subposet of this guy, equivalently an additive poset, let's say A. A is plane. If A embeds in this power set additive posets in 2 to the power I for finite set I. Yeah, here everything is finite, just for simplicity. For finite set I. Now, what does it mean, embeds? Embeds means that we take an additive subposet of this guy, which is just a subgroup or subvector space with restricted partial order, and then A should be isomorphic as an additive poset to this subgroup. Now, one question I have is whether it is true or not that all additive posets, let's say finite, are plane. So I don't know any example of an additive poset which doesn't do it, which is not obtained by that construction, or equivalently, which is not isomorphic to. So that's a question. In any case, in topology, we consider only plane additive posets, only they arise. So from now on, we can focus on additive posets. Let's set up plane. And by the way, for such plane additive posets, we can define a numerical characteristic, which I call complexity. So the complexity of a plane additive poset is the minimal number of elements in such a set I. Is the minimal cardinality of a set I such that A embeds in 2 to the power I. That's a non-trivial invariant, difficult to compute. Equivalently, you can define it as a minimal number of elements in the set S, such that A arises from S. So S is a subset of the dual vector space, and A arises from this particular subset by the construction which I described. So it is the same number, which is the complexity of A. So this is it is let's suppose everything is finite. So if A is finite, or finite dimensional Z2 vector space, set R is finite, everything is finite, just for simplicity. But there is a version for... Here it is finite, right? For a finite set. So such an additive poset is necessarily finite, because it embeds in a finite poset. So that's an interesting invariant, interesting to compute, difficult. Well, there are quite a number of other invariants which come from the theory of posets. If you just know a little, they have heights, they have widths, and some other interesting numerical characteristics. So they all apply, and interesting to discuss. Okay, now I want to give a couple more definitions. The next definition is the one of an atom. So an atom in an additive poset in an additive poset A is an element such that the set of all elements B of A that are smaller than or equal to A consists of only two elements, 0 and 8. There are no elements smaller than or equal to A except 0 and A. Then A is called an atom. Well, that's a standard notion, more or less, the theory of partial ordered set. Now, why atoms are interesting in this case? That's a theorem. Suppose that, again, A is finite. If A is a finite additive poset, then every element of this A let's say every element H of A expands as a sum of atoms in a canonical way. No, the way is not unique. So what does it mean? It means that atoms, of course, generate A as a vector space, but they don't constitute a basis. There are many of them. In general speaking, they generate this vector space, and there is a canonical expression for every element H as the sum of the atoms. Canonical, which means it is determined uniquely by the partial order and stuff like this. So this expansion uses so-called Möbius function. I'm not going to use the Möbius functions. So H expands as a sum over all atoms A of this additive poset with coefficient equal to mu HA, where mu is a so-called Möbius function. So there is a unique expansion there is a canonical expansion, but there may be others. Right? All right. Now, of course, this theorem, which is not difficult to prove, one just needs to know what is Möbius function, how to work with it. Of course, it raises question of uniqueness of such an expansion. It is not unique. And to define, well, to go further, I want to introduce another definition, so-called independence. So two elements, A and B, of an additive poset A, are independent from each other. If A is smaller than A plus B. If A is smaller than A plus B. Now, this is symmetric relation. So if A is independent from B, then B is also independent from A. That's a symmetric relation which replaces, in an example. Let's take an example when A is 2 to the power I. Elements are subsets. When two elements are independent, these are two subsets. Independent means just disjoint. So A and B are independent. A and B are independent. If and only if they are disjoint as subsets of I. They are disjoint. So this notion of disjointness of subsets extend in this way to arbitrary additive posets. By the way, I want to say what are atoms here. So atoms are just one element subsets. One element subsets. So, and indeed, so this theorem, of course, is obvious. And it says, in this example, it says that every subset of I, for example, is a union of its one element subsets. Nothing more than that, which is obvious, but this is more general.
In the composition of R. What is this?
Mu is a Möbius function, which I didn't define. Okay. Now, so this theorem has versions in which you require atoms in this expansion to be pairwise independent. So the theorem says that every A, every whatever it was, H, expands as a sum of pairwise independent atoms. So you can expand any element as a sum of pairwise independent atoms, but this expansion is not necessarily unique. There may be many ways to do that. All right. So that was about all I want to say about the algebraic part. Now I come back to graphs. And in fact, more general to CW complexes. So let's consider a CW complex. So consider a CW complex X, a CW complex of certain finite dimension, for dimension n. And the following vector space A is as an n-dimensional homology of X with Z2 coefficients. So the highest dimensional homology. And my claim is that there is a natural partial order here, which makes it into an additive poset. So in fact, there is an additional structure here, namely the structure of an additive poset. Now how it is defined? It's defined very simply. So what is a n-dimensional homology? Now recall the cellular chain complex. So homology is the homology of the cellular chain complex of Ax. Now this guy is the leftmost group. So there is nothing on the left of Cn. So that's the boundary homomorphism. So this is just the kernel, therefore, of the boundary homomorphism of the chain, of the cellular chain complex of X. Now, what is Cn? Cn, elements of Cn form a linear combination of n-dimensional cells. So this space, this is a vector space over Z2 with a specified basis. The bases are just n cells. So this is nothing else as additive poset 2 to the power I, where I is a set of all n cells of X. Right? So every cycle, every element of the kernel is just a finite set of n cells, such that actually every element of Cn is just a set of L cells, a finite set of n cells. Okay, now this is an additive poset. This is a subgroup. So this is subgroup of Cn. So it's an additive poset, and that's it. This turns n-dimensional homology into an additive poset. Of course, it's not a homotopy invariant of this complex, but this we knew already from the beginning, that the invariants we need are not homotopy invariants. On the other hand, it is preserved under subdivisions of X. So if you subdivide X, you get the same additive poset. Right? In particular, this applies to graphs. So if X is a graph, a one-dimensional CW complex, then H1 of a graph with coefficients in Z2 is an additive poset. And now I can answer the question I stated at the beginning. The question, the answer is, again, you can guess it now. So if you have a graph gamma, let's say finite graph. Gamma is a finite graph. So that's the theorem. An element A of H1 of gamma with coefficients on Z2 is realized by an embedded circle in gamma. If and only if A is an atom. So this language of atoms is actually a somewhat fancy way to say, to speak about embedded circles in graph. That's a simple theorem. There is nothing deep in it, just a little argument. However, there are deeper results, and I want to mention a couple. So the first question you may ask, looking at this construction, is what additive posets can be realized in this way? Suppose you start from a, let's say, finite additive poset. So let A be a finite additive poset. And you ask yourself, is there a CW complex of dimension n such that this is A? And the answer is that for any n greater or equal to 2, there is an n-dimensional CW space, or CW complex X, such that the n-dimensional homology group of X with coefficients in Z2, now viewed as an additive poset now by this construction, is isomorphic to A. So in any dimension, starting from 2, every additive poset, finite at least, every additive poset can be realized. You are right. It is plane. Instead of saying finite, I should have said plane. Very good remark. It is plane. Plane means it embeds in 2 to the power I for some I. And that's why it is interesting to know whether there are non-plane. Yeah, by the way, I forgot to say this is always plane by the very definition because it is an additive subposet of this. So it is plane. That's why it is interesting to know if there are non-plane. And in this theorem, we talk about plane. Now, quite interesting, what happens when n equal to 1? For n equal to 1. Now, I don't know a complete answer. That's an interesting story. But I can say something. So for n equal to 1, the theorem is not true. Not every finite or plane additive poset can be realized as one-dimensional homology of a graph. And that's the next theorem. Let's consider just the additive poset, let's say finite additive poset. A. With partial order beyond the trivial partial order. So A is an arbitrary Z2 vector space of finite dimension. And this is, remember, the trivial partial order where only 0 is smaller than other elements. And that's all. So such a finite additive poset is realizable by graph. Let's say it's realizable by graph, which means there is a graph whose additive poset is isomorphic to this one, if and only if the dimension of A is greater than or equal to 4.
You said great number, you wrote less.
Less than or equal to 4. Of small dimension. 1, 2, 3, 4 are realizable by graphs, but 5 not realizable. 5 not realizable. Okay, now how to realize for small dimensions? When dimension, let's say, is, for example, this graph I started at the beginning. it realizes the dimension of A equal to 2. What? Is realizable by a graph if and only if the dimension of A is smaller than or equal to 4. That's the statement.
Yeah, but what happens if you take a graph with an H1 dimension 27?
Then it is not realized. There is no such graph with this additive poset. That's an additive poset. What does it mean realizable? It means isomorphic to the additive poset of the graph and with coefficient Z2, and isomorphism means order preserving isomorphism. This is an additive poset.
So the point is that you have a trivial number.
What is trivial? There's a trivial order, which is defined by the condition 0 smaller than or equal to A, smaller than or equal to A for all A. So this is only for the trivial. That's a theorem which deals only with one specific class of very narrow class, not for arbitrary. So this graph realizes. If you look at this of the additive poset of this graph, it has a trivial order. All atoms are atoms except 0. All non-zero atoms are atoms. So there are no relations between different elements. So that's this graph. One skeleton of a tetrahedron realizes dim A is equal to 3, right? Because the Bethe number of this graph is 3. And the dim A is equal to 4 is realized by K33. So that's a graph with 6 vertices. And each vertex on the top is connected to each vertex in the bottom. So that's a graph K33. And again, the partial order, all elements of H1, all non-zero elements are atoms. And the Bethe number is 4, I believe. And then, if the dimension of A is starting from 5, then there is no such graph. So that's, of course, another question to try to give to characterize those additive posets that are realizable by graphs. Okay, so yeah, you have to prove it. That's a theorem. You have to deal with it. Is that realized? No. No, you can always add something like this, for example. H1 doesn't change.